In the previous lecture, we have discussed the several types of the equation of plane, that is the equation of plane having perpendicular vector and the passing through point, equation of plane passing through point and parallel to the two vectors, and the equation of plane passing through 3 points. Now, today we discuss the next form of the equation of plane, that is the equation of plane in a normal form. Okay, here we know that the equation of plane, okay, when plane passing through point A bar and perpendicular to the vector n bar, then the equation of plane is r bar dot n bar is equal to a bar dot n bar. It is the equation of plane, okay, passing through point and perpendicular to the given vector. Okay, then r bar dot n bar is equal to a bar dot n bar, and here r bar is a variable point. Okay, a bar dot n bar, a bar is a given point, that is a plane passing through point, and it is a perpendicular vector to the plane, that is the normal. Then the dot product of these two vectors, it is a scalar. Okay, therefore this vector equation of plane we can write r bar dot n bar is equal to d. It is a vector equation of plane. Now we see the vector equation of plane in a normal form. Here it is a normal form, r bar dot n cap is equal to p. Okay, here normal form equation, see carefully, it is r bar dot n cap is equal to p. Okay, here difference between these two vector equation of vector equation of planes, it is r bar dot n bar is equal to d. D is a scalar, and r bar dot n cap is equal to p. P is also scalar, but here p is a distance of plane from the origin. Here this d, it is not a distance of a plane from origin, but in this equation it is a p is a distance of plane from origin. Here it is a r bar dot n bar, it is a normal vector, but it is r bar dot n cap, it is a unit normal. Okay, here so to find the vector equation of plane at a distance p units from the origin, that is the distance of a plane from the origin, it is a p units, and to which a unit normal n cap. Okay, here we consider a plane. Okay, it is a one plane, then it is a normal. Okay, here, and then suppose it is a O and it is n. ON is a normal to the plane, see carefully, ON is a normal. Okay, then we have the unit vector along the normal. Okay, suppose it is a n cap, it is a unit vector along normal, it is ON, O to n, it is a point n, it is a foot of perpendicular. Okay, and then it is a point, and here given that the distance of a plane from origin, that means distance between these 2 points, it is a p. It is a given distance between these 2 points, that means distance of point from the origin, distance of point, this foot of perpendicular, distance of point n from the origin, it is a p. That is a distance of a plane from origin, it is p, it is given. Okay, that means vector on, okay, see carefully, vector on is a position vector of point n, because it is n and it is origin. Okay, we know that the position vector of point, it is a vector drawn from origin to the point, it is a position vector, therefore it is origin, and it is n is a foot of perpendicular. Vector on is the position vector of point n. Okay, now we consider any point on a plane, it is suppose r. Okay, then ON perpendicular to NR, ON perpendicular to the NR, it is NR, this line completely lie on a plane, and it is ON is a perpendicular to the plane, therefore ON perpendicular to the NR. Okay, now here let it is a ON is perpendicular to plane. See carefully, ON is a perpendicular to the plane, and distance of a plane from origin is, it is a p, distance of plane from origin, that means length ON, therefore ON, it is a length ON is equal to p. Okay, n is a foot of perpendicular. Okay, here first we can write n is a foot of perpendicular, then we can write this. Okay, here ON perpendicular to the plane, therefore N is a foot of perpendicular. Okay, N is foot of perpendicular from origin. Okay, therefore length ON is equal to P. Length ON is equal to P, and then position vector of point N is, it is a N bar. N bar is a position vector of point N, that is ON is equal to N bar. Okay, because N is a foot of perpendicular and ON is a vector drawn from origin to point N. That means ON is a position vector of point N, and that denote we can N bar. Now length ON, okay, here let N cap is unit vector along N bar, that is the ON. N cap is a unit vector along, it is ON. That means N cap is a unit vector along N bar. It is a N bar, and N cap is a unit vector along N bar. And here ON is a perpendicular to the plane, therefore N cap is also perpendicular to the plane. Then see carefully here. N cap is a unit vector along this, and P is a distance. That means it is a direction and it is a magnitude. Therefore we can write vector ON is equal to distance, that is a magnitude, and direction. It is a direction as well as magnitude. Vector ON, and vector ON we can write N bar. That means vector ON is equal to P into N cap. Okay, now it is a let it is R with position vector R bar be any point on plane. Okay, therefore it is a NR perpendicular to N bar, therefore perpendicular to the N cap. NR perpendicular to the ON, therefore NR perpendicular to the unit vector N cap, that because N cap is a unit vector along ON. This, okay, then and therefore we can write NR dot N cap is equal to 0. If two vectors are the perpendicular, then their dot product is 0. Then we can write in the position vector form R bar minus N bar dot N cap is equal to 0. Therefore R bar minus, it is N bar, P into N cap, dot N cap is equal to 0. N bar is a position vector of point O, it is position vector of point N, that is ON is equal to N bar, and ON is equal to P into N cap, and then take a dot product. R bar dot N cap minus P into N cap dot N cap is equal to 0, and then R bar dot N cap minus P is equal to 0, and therefore R bar dot N cap is equal to P, and then it is the vector equation of plane in a normal form, where R bar dot N cap is equal to P. Now here P is a distance of a plane from origin. This constant R bar dot N cap is equal to P. When the normal is a unit vector, then is this constant, this scalar is a distance of a plane from origin. This is the equation of plane in a normal form. Here normal is a unit vector. Okay, see carefully. here it is the equation of plane in a normal form. Okay, here n cap is a perpendicular to the plane, that is it is a unit normal, and it is a p is the distance of plane from origin. Okay, here we know that the equation of plane is r bar dot n bar is equal to d. Okay, r bar dot n bar. Okay, here it is a n cap. Here note that some remarks. Here the equation of plane r bar dot n bar is equal to d is not in a normal form. Okay, here it is r bar dot n bar is equal to d, it is a n bar. Okay, so this d is not a distance of a plane from origin. When the n bar it is a n cap, that means unit normal, then the constant is a distance of plane from origin. Here r bar dot n cap is equal to p, therefore this p is a distance of plane from origin. Now to reduce this vector equation of plane in the normal form, we divide the magnitude of n cap, that means it is a n bar is a vector. We want to find the unit vector along the n bar. We know that unit vector along n bar, it is a n bar upon magnitude of n bar, it is a n cap. So we divide this equation by the magnitude of normal. Okay, here to reduce this equation in normal form, divide by it is a magnitude of n bar. Okay, therefore we can write r bar dot n bar upon magnitude of n bar. Okay, 1 upon magnitude of n bar, it is a scalar. Okay, then d upon magnitude of n bar, and therefore this can be written as r bar dot n cap is equal to, it is a d upon magnitude of n cap, so it is p. Okay, since it is a p is equal to d upon magnitude of n bar, that means when the given equation in the form of r bar dot n bar is equal to d, and the question is asked find the distance of a plane from origin, then distance of plane from origin, this scalar or this constant is a distance when the magnitude is a unit, it is normal is a unit vector. So we divide by the magnitude of normal, and then divide this scalar by the magnitude of normal, then the quantity, it is a d upon magnitude of n bar, it is the distance of a plane from origin. Okay, when the equation is not in the normal form, we reduce this equation in the normal form. Okay, and this is a distance d upon magnitude of n bar, it is a distance of a plane from origin. Okay, this d is not a distance. When normal is a unit normal, then this scalar is a distance. Okay, now it is a equation, it is a vector equation. Now we find the by Cartesian equation. Now equation of a plane in Cartesian form. Okay, here ax plus by plus cz plus d is equal to 0. That means this d, that is a distance, it is a mod of d. This d is not a distance of a plane from origin, because a, b, c are the direction ratios of a normal, okay, which are not a direction cosines. Okay, so we divide throughout. Okay, here to reduce it in normal form, divide by it is under root of a square plus b square plus c square. That means divide by magnitude of n bar, it is a, b, c are the direction ratios of normal, then the normal is a I cap plus b j cap plus c k cap, and then the magnitude of normal, it is under root of a square plus b square plus c square, and then this becomes, see carefully, this becomes a upon this a square plus b square plus c square, b upon under root of a square plus b square plus c square. Okay, here we can write here a upon under root of a square plus b square plus c square x plus b upon under root a square plus b square plus c square y plus c upon under root a square plus b square plus c square z and plus d upon under root a square plus b square plus c square is equal to 0. And then we know that a upon under root a square plus b square plus c square means L, that is Lx plus my plus nz and plus it is a p is equal to 0, where p is equal to d upon under root a square plus b square plus c square, and then it is L, m and n are the direction cosines. We can write here. Here, see carefully, it is L, m and n. Are direction cosines of normal. Okay, and direction cosines of normal, that means Li cap plus mj cap plus n k cap is equal to n cap is unit normal. Okay, and in this Lx plus my plus nz plus p equal to 0 is a Cartesian equation of plane in a normal form. Therefore, Lx plus my plus nz plus p is equal to 0 is Cartesian equation of plane in a normal form. Okay, where this p, that means the mod of p. Okay, p, it is a scalar. By calculation it is becomes also negative, but it is a distance, therefore it is a mod. Therefore mod p is a distance of plane from origin. Okay, here see carefully, it is a Cartesian equation of plane in a normal form. It is a Cartesian equation of any plane. Okay, ax plus by plus cz plus d equal to 0, and it is a Cartesian equation of plane in a normal form. Okay, it is a vector equation of plane. It is a vector equation of plane in a normal form. It is a Cartesian equation of plane. It is a Cartesian equation of plane in a normal form. Okay, now the third note here. It is the first vector equation of plane. It is a vector equation of plane in normal form. Second, Cartesian equation of plane. It is a Cartesian equation of plane in a normal form. Now we can find the foot of perpendicular. Okay, here foot of perpendicular drawn from the origin. Okay, here the coordinates of foot of perpendicular. Okay, and in last theorem we can take the foot of perpendicular, it is a n. Okay, now the coordinates of foot of perpendicular drawn from origin are, see carefully, it is LP, NP, MP. Here L, M and N are the direction cosines of the normal. L, M and N are the direction cosines of the normal, and P is a distance of a plane from origin. Then the coordinates of the foot of perpendicular LP, NP, MP. Okay, L, M, N are the direction cosines of the normal. Okay, and P is a distance of plane from origin, and then are the coordinates of foot of perpendicular. Okay, see carefully these three remarks. Okay, and the theorem. In the next lecture we see the examples of the equation of plane in a normal form.